periodic table a lot today, so I thought I would inspire you first with some cool ones. Video game characters, look. Hold on, where we? Sonic, Chromium, oh, Kirby, Zelda, Mario. Look, if we can come up, if somebody would make me a periodic table like that, that'd be awesome. And then this one was just cool. I like interior design, colors. There you go. So we're going to talk about the periodic table a lot today. So let's go ahead and jump right in. Your paper that I gave you has a little bit of information on isotopes already. This part's not on there, but you're going to see a big chart eventually. And versus you drawing a big chart out, I actually did it for you. So we can kind of do the learning part, not the writing every single thing down. Okay, so we already know about atomic structure. It's something we talked about back in 7th or 8th grade a little bit. Subatomic means below or within the atom. What are the three parts that are subatomic? Shout it out. Protons, neutrons, electrons, okay? Which ones are in the nucleus of the atom? Protons and neutrons. Electrons are on the outside, and that's what we've learned from our, advancement of the scientific atomic model, that the protons and neutrons live on the inside, and the nucleus and the electrons live on the outside, okay? So, subatomic particles are protons. How do you know the number of protons? Immediately when you look at the periodic table, you look for the atomic number. So you should be able to look at anything and tell me the number of protons. So, periodic table's in front of you. Tell me the number of protons in zinc.
30.
Zinc is 30. Good job, because it's the 30th element over as you go row by row by row, which is the atomic number 30. Okay, if we knew that protons are a positive charge, a 1 positive charge, electrons have to counteract their charges, and we say that they have a 1 negative charge. So, if I have a neutral atom, what does that mean about my numbers of electrons and protons? They're the same, right? If it's neutral, they totally negate each other. So, if I have a neutral atom, like if I just say zinc, just plain old zinc, I'm going to have, how many protons did you say I would have?
8.
Zinc was number 30, right? You'd have 30 protons and how many electrons? If it's neutral. Counteract it, people. 30, okay? I like you to shout out some information to me, okay? So if you're looking at zinc, you say, okay, it's got 30 protons, and if I have to tell you if it's neutral, it has to have 30 electrons to balance out that charge. So that's just neutral atoms, though. We'll get to neutrons in a second. So if I didn't have a neutral atom, I would consider that an ion. Ions come in two varieties. Am I going, is that up too far? These are okay. Okay. Ions come in two varieties, cation ions and anions. Cation ions, how do I remember the cation ion is a positive charge? What's in there that looks like a positive charge? Right, the T. So you can tell that the cation is the positively charged ion, and the anion is it just sounds negative, right? Anion. So I remember that is going to have the negatively charged, or negative charge on it. So, rule though that we all have to remember is ions come from changing the electron number. Never can you change the proton number. Protons. Okay? You can never change protons, because if I say I have zinc and you told me zinc has 30 protons, and you go, oh, I just want to take one of those protons. You take one, we're down to 29 protons. We're no longer zinc. Who are we if we have 29 protons? Copper, right? We're backing it up on the periodic table. So if you change the number of protons, you have totally changed the identity of the element. Therefore, you are only allowed to touch electrons. And that kind of makes sense, because if the neutrons and protons are in the middle in the nucleus, and the electrons are kind of around here, who's easier to grab if you're trying to take something? Definitely the electrons, because they're in the outside perimeter, where the neutrons and the protons are on, like, really condensed in that dense core. There ain't no way you're going to pull one of those out. So you're going to have to take an electron. That's the only thing we're allowed to change when dealing with the subatomic particles so far. Okay, so if I'm a cation, how did I get this positive overall charge on myself? Well, what's happened is, originally, let's go with magnesium here. How many protons does magnesium have? Look at magnesium.
12.
12, okay, because it's the 12th in the atomic number. I'll have to turn the lights back on, actually, because I know it's probably hard to see, but the paper, or the green paper, is not really help. Alright, so it's got 12 protons. Okay, if I have 12 protons and I'm neutral, you see there's no charge indicated here. How many electrons do I also have? 12, right? Okay, now what's happened here is I'm not allowed to change protons, right? So this magnesium 2+, which is an ion, happens to be a cation ion in this case because it's positive, it has to remain at 12 protons, because if you change the proton number, we've totally screwed up the atom. So what has to happen is these electrons two of them have to be lost. Because if I lose 2 electrons, how many electrons do I have then? 10, thank you, 10 electrons. So who's winning here, 12 or 10? 12, so you can see that the difference here is I have 2 more protons than electrons. So that's how I get that 2+ charge. Does that make sense? Okay, it's only because the 2 more protons means I have 2 more pluses than I have minuses. So that overall creates a 2+ charge. Notice I didn't change protons, I only changed electrons. Okay, that means those electrons went to somebody else. And that's what helps create a bond later in life here, okay? So, anions are going to be different. Anions have that negative charge. So overall, they have an overall negative charge, meaning they have to have more electrons than they have of their protons. So, how many protons does oxygen have? Periodic table. Oxygen's upper right corner. 8, okay? So it has 8 protons. And if it's a neutral oxygen, how many electrons does it also have? 8, okay? So it's got 8 electrons. And now if I'm going to go to oxide, which is this oxygen 2- ion here, how many protons does it have? Who said 10? Shame, 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 shame. You can't change the protons. You still got to keep the same protons because they represent, like they are saying, I am oxygen if I have 8 protons. Never change the protons. So if I have an overall 2 negative charge, how many electrons do I have? 10, because I need to have 2 extra negative charges to leave overall a 2 negative charge. So this one is showing 2 extra electrons equals a 2- charge. All right, so those are ions for us. I haven't talked about what yet, though. So about protons, protons, electrons. Haven't really talked about neutrons too much. Okay, so hidden neutrons now, and then we're going to talk about how that relates to isotopes. So these were ions. Ions have charges. Isotopes are going to be something that have a different number of neutrons. People get ions and isotopes mixed up, so you got to kind of separate those two things in your notes. Make sure that you know if we're dealing with ions, that means we've changed up the electrons. Now we're going to deal with neutrons and kind of get into isotopes here. So neutrons are those neutral peacekeepers in the nucleus. They have to keep peace in the nucleus because if you have all those pluses together in the nucleus, all those protons, they start to repel each other, like 2 ends of a magnet. You take 2 ends of a magnet. Actually, I don't know if I can do this. Okay. These are neodymium magnets. I'll pass these around. Don't eat them. They're toxic to your digestive system. I had to bring them to elementary school and put them in baggies because I was afraid they were going to swallow them. So anyway, 2 ends of the opposite ends of the magnet. I actually am not doing this. I really can't put these together. Okay. It won't happen. They're repelling each other. But if I put two of the, sorry, I turned this one too. 2 of the opposite ends, a positive and negative pole, and it's going to come together. So protons and protons repel each other like crazy. So those neutrons are in the middle, being peacekeepers, because this is going to happen. It's going to make the atom explode. So, play, but I want these back. Don't swallow them, as I said earlier. Okay. So anyway, neutrons are going to be, you can actually look and calculate the number of neutrons from an atom based on this formula. Mass number. How do you get the mass number? Where would one find the mass number? On the periodic table, right? So give me the mass number of zinc. .39. Okay, and those are called atomic mass units, but I'm not going to put a unit on that right now. So sometimes you'll be given decimals, and I'll tell you why that is in a minute. But the decimals occur due to like different numbers of isotopes. So I'm going to round this to 65 because I need a whole number, because I can't have like half of a neutron or half of a proton or half of an electron. Those all come in whole integer increments. Anyway, so the mass number of zinc is 65. What was the atomic number of zinc again? 30. So how many neutrons does it have? 35 neutrons. And that's just showing you that you can do the math or you can actually be given the number of neutrons and go back and find the mass. So you can go both ways here. Okay. So isotopes, let's go ahead and this is on, I think I copied this on the paper for you. Get at least the little table thing here, but you want to write down what isotopes are too. So isotopes are going to be, it's the same atom. It's literally, sorry, it's the same element. It's zinc, it's zinc, it's zinc, it's zinc. But the element zinc can come in multiple varieties. And the reason I know it's the same element is because I literally am saying the same number of protons. So it's the same element. Because if you change the protons, then you change the element. But we're going to have a different number of neutrons. So what does that actually change? If I change the neutron count, what is that then going to change? What of the atom? Yes, the mass. It's going to change the mass. So if I change the numbers of neutrons, those are the only things that weigh anything. So that's why it constitutes a change in mass. Don't forget that the mass, I didn't actually say this earlier, the mass is made up of protons plus neutrons. Electrons are so itty bitty, we say they're negligible. In mass, they're very, very small. So we just ignore their mass. So the mass number is made up of protons plus neutrons. So if I can't change the protons, that's good. If I change the neutrons, then therefore the mass will change. So isotopes just have different masses. That's it. Same element, different masses. All right. So in this one, you can designate an isotope in multiple ways. So I'm going to walk through this one first, and if you need to make any additional notes, do so. But this is nitrogen, right? What is this top number representing? I know you can see it, but verify it on your periodic table as well. You see nitrogen on your periodic table? What atomic number is it? 7. So it's right next to oxygen, right? You see atomic number 7. If you look on the periodic table, it says it says 14.007. Why does it say 15 here? What are we talking about right now? No, not figures. They don't do that to me right now. What is the title of this slide? Isotopes. So I have shown you an isotope of nitrogen. It's not the most common isotope of nitrogen, because the most common isotope of nitrogen is going to be nitrogen 14, as indicated on the periodic table, because the periodic table shows you the most common form of that particular element's isotope. So I'm showing you just another version of nitrogen. It's still nitrogen because it still has an atomic number of 7, meaning it's got 7 protons. But I have an isotope, meaning what did I change to get 15 instead of 14? Number of neutrons, right? So this is just an isotope of nitrogen. I also have said I have a different charge. So that means it's also an ion of nitrogen. So this is an isotope that is also an ion because I have changed the number of what to get this charge different? Electrons, because you shall not change protons, okay? So the protons always stay the same. And how did I get the charge? I lost 3 electrons. And how did I change the mass? I gained 1 neutron, or I have a different number of neutrons. So you can see a lot from something simple as that. You just have to be able to dissect that information. There's a second way to note isotopes, though. This one's really small, but that's uranium-238. So uranium-238, what do you think that 238 standing for? Mass, right? Find uranium. Periodic table. It's towards the bottom. Find it. What atomic number is it? 92. Good job. So I can write it like this. Why is it okay for me to write it like this? Because I don't have to tell you the atomic number. If I tell you the element, do I have to tell you the atomic number? No, that periodic table is your BFF. You will have it at all times. I'll never deprive you of it because it's a tool you need to learn how to use. Ladies, I hope you're listening to some of these things too, okay? So you can look up the atomic number and you can find, oh, well, uranium's number 92. So what does that mean about it? 92 protons. Okay, if you see that it's neutral, you don't see any charge here, right? That dash is not a negative. So what does that mean about electron count? Also, yeah, also the same. So number of electrons is 92. So how do you figure how many neutrons it has? Subtracting, right? Subtracting what? Subtracting. So what is this representing? Mass number, right? So you take the mass minus the what?
Proton.
protons to get the neutrons. Good. Because if mass was protons plus neutrons, then what you would say is 238 is equal to 92 plus neutrons. So you're going to subtract 92 from both sides to get your neutron count. So that's like 3 plus 8, 146, I think, neutrons. I think so. So it's not that bad. You just have to remember mass is equal to protons plus neutrons. And we're good. So these two pieces of information, I don't think I have those on your paper, do I? Nay? Okay. This is really important. If I ask for the Z number is going to be used more so in the next week. If I ask for the Z number, it is the atomic number. So if I ask for the Z number, I'm actually asking for the number of protons. And this is going to eventually be us writing it in A to Z notation, and I'll show you that in just a second. If I ask for the A number, that's me just asking for the mass. Don't forget, mass is protons plus neutrons. So I know you want to go, oh no, I don't know why you'd say that. Okay, A number is atomic mass. Z number is actually referring to something called ZEF, nuclear effective charge. We're going to talk about that next week, but it's the number of protons. So just remember Z protons, A mass. Okay, so when I say write the A to Z notation, what I'm talking about is if this is your element, which of them went on top on my previous example? The mass or the atomic number? The mass, right? The mass is the higher number. So if I want you to write the mass on top, that's called the A number. The atomic number, which is the proton number, goes on the bottom. And my element is X here in this case. So this is called A to Z notation because it's literally A to Z, the way it's written top to bottom. So if I want you to write the A to Z notation for carbon 14, you write carbon 14. What am I saying when I say that? Mass number, right? So it's 14. And because I don't have to tell you the atomic number, you got that best friend in front of you. What's the atomic number? 6. So that's the A to Z notation of carbon 14. So when I say A to Z notation, I want it to look like that. Cool? All right, let's keep going. This is going to be the part where you guys have a big chart. Oh, yeah, we'll do the big chart first. Okay, you have this. We're going to go through a couple of different types of examples, so you're very proficient in this. And right all over that paper, that's why I printed it for you, okay? So, let's go for this. You will need your periodic table, so make sure it's out there. So, starting really small, we have hydrogen. Is this an atom or an ion? Looking at it, atom or an ion? It's just an atom because you see no charge, okay? So that's just identification. What is the atomic number of hydrogen? 1. What is the atomic mass of hydrogen on the periodic table? What is it? 1.008, and that's in AMU's atomic mass units. That's really close to 1, I know, but that decimal occurs because everything on the periodic table is an average of multiple isotopes. You'll never ever find an atomic mass of hydrogen being that exactly. Like if you could just go pick up a little atom of hydrogen, you wouldn't find that because that's an average. So whenever we look at the atomic mass, we get that from the PTOE. When we want just the mass number, it's usually going to be given to us, or we'll round this one to the closest. Because the mass number must be a whole number, no decimals at all. Mass number must be a whole number, no decimals. Atomic mass is whatever PTOE gives you, you got to take it. All right, so if I know that the atomic number is 1, the mass number is 1, how many protons does it have? 1. How did you know that? Same as what? Yes, protons are the same as the atomic number. So whatever is in this column here should be exactly the same as what's in this column. No choices, because you're never allowed to change protons. So if you're going to go, okay, well mass is equal to protons plus neutrons. I know it's tiny there. Mass is equal to protons plus neutrons. Well, how many neutrons does it mean it can have here? Huh? 0. Because if you got 1 as your atomic number, that's your number of protons. You have also 1 as your mass number. That means 1 is equal to 1 plus blank. It's got to be 0. So you have 0 neutrons in hydrogen. That's okay, it's really tiny. It's got very little room for anything else. Okay, so it's neutral, you can see. So how many electrons does it also have? 1, thank you. It's got 1 negative charge to balance this 1 positive charge. That's why it's neutral at 0 charge over here. All right, so the next one we've changed. We went to is it an atom or is it an ion? Definitely an ion. Okay, so this is the same. Atomic number is still 1 because it's still hydrogen. I'm going to go ahead and say, okay, if I know the atomic number, what else do I know? Proton number. I'm going to immediately fill out the proton number when I fill out the atomic number. Also 1. Okay, atomic mass here, still the same, so it's 1008. But when I'm trying to figure out the full mass number, I'm going to go ahead and say assuming 1 because we rounded down to 1. All right, so I see this positive charge. Oh, sorry, I haven't done the neutrons yet. So the mass has not changed, nor has the number of protons. Therefore, this is still going to be 0 for your protons because 1 is equal to 1 plus blank, so it's got to be 0. I mean neutrons. Okay, so now, what do I do with this positive charge thing here? What has changed? I minus 1 electron to make sure that I have more protons than electrons. Because previously I had 1 proton and 1 electron. But now I'm here, so I need to have a positive charge. So I keep my protons and I drop an electron. So that happens to be how many electrons now? 0. 0 electrons. 1 electron. There we go. Okay, let's do a harder one. What does this 2 refer to? Mass. Thank you. So where am I gonna put that? Right here. Immediately, I'm identifying the mass because if I see H-2, that's not raised to like the -2. That's not a charge. It's a dash. So this is an isotope. Because if it gives me the mass like that, that's an isotope of hydrogen. This is called deuterium. It's heavy water, something that some people have problems with in their homes. Okay, so, or it composes heavy water. Anyway, so we have isotope, mass of 2. What's the atomic number still? 1, because it's hydrogen. So what else do we know? Proton number still. Okay, I'm going to, since it's identified the isotope 100%, I don't really care about the PTOE because I actually have given the mass. So I'm just ignoring the atomic mass here because I don't need to look it up. It's given to me. All right, so let's go ahead and do the neutron number. What are you doing in your head right now? What minus what? Right, mass, which is 2, minus protons, which is 1. So you get 1 for your neutron. That makes sense because your mass is 2, so you have 1 of each, 1 proton and 1 neutron. How many electrons? How many? 1, because it's a neutral compound, neutral atom. So your protons must equal your electrons. So protons of 1 equal your electrons of 1. All right, let's keep going. This one's getting a little bit more complex here, okay? So we have oxygen. We have some A to Z notation going on, and we have this -2 here. Let's start with the atomic number. Which of these is the atomic number? 8, because you remember that 8 is the A to Z. The Z number, that's your proton number. So I can automatically go figure out what now? 8 is also the proton number. Was that this column? No. This one? This one? Sorry, okay. All right, so 8 is also your proton number. What is the mass number here? 16, good. So the mass number's up top, 16, and that was here. So do I care about periodic table? No. Scratch that. All right. And then I see, I'm going to go ahead and go straight to electrons on this one. I see this -2. What does that mean? 2 more what? Electrons. So I originally, assuming neutral, 8 protons, 8 electrons, right? But now I'm like, oh no, it's not neutral. I've got 2 more electrons, so I've got to go bump it up. So how many electrons? 10 electrons. And what's the mass number? I'm sorry, what's the neutron number? 8, because you did 16 mass number minus 8 protons is 8 neutrons. All right, pick another one we can do, because if you get the hang of it, I'm going to let you guys do this by yourself. I'm sure there's one I want to do. Let me pick one more, and then I'll let you guys actually pick. Let's just do magnesium, just the one word magnesium. So magnesium, atomic number what? 12. So what does that also mean? 12 protons. That was here. Okay. How many electrons? How many? 12 again, because you see there's no charge indicated here. So protons must equal electrons. Okay. What is the mass, atomic mass from the periodic table? 24.31. Okay, that's what the atomic mass from the PTOE is. Well, we need to round that to what? 24, because we need a whole number to use for mass so we can get the true number of neutrons. So how many neutrons? 12, because you did 24 minus 12 is equal to 12. So the reason that you're seeing a lot of times equal protons and equal neutrons is because that leads to the most stable situation for atoms. It's not always going to be that. Like when we previously did uranium-238, I mean, it gets really, you get a lot of numbers of neutrons if you go to bigger atoms. But these little atoms, like first, second, and third row, they're pretty dainty. So we have a lot of times equal protons and neutrons, but don't expect it. Just see that trend. All right, let's do, you guys work on those. Work together. Take about 10 minutes, finish that chart up. I'll be around if you need me. Some of you guys probably did most of it while I was teaching still. You can check anything that you need to if you had a question on one. Haven't done the last one yet because I did not pull my board up enough actually. I think the harder of these, the calcium 2+ one, was the only tricky one really because you had to look up the periodic table elements. So you got 20 for its atomic number, leaving you with 20 protons, and then you had to look and you saw, okay, 40.008 rounds to 40 for your mass number. So that was not bad. 40 minus 20 is 20 still. Your neutron number should be 20. And then you had to go, oh, okay, 2+ charge means I have more protons than electrons, but you shall not change protons, so you had to subtract 2 of your electrons you previously had, so it went from 20 to 18. And then magnesium, we had just kind of done, but I'll run through this again. 12 for its atomic number, so 12, so it's for its proton number. Atomic mass not needed, but mass number is 26, leaving you with 14 neutrons, because 26 minus 12 is 14. And then previously you had 12 electrons because it was neutral, but seeing it's a 2+ charge, it means you only have 10 electrons. I'll pull this back up if you need it later. Who feels good about this? Give me a thumbs up if you feel like this is something you are capable of. Cool. Okay, some of us will need some more help with this. I'm going to kind of move on with my majority here. We're going to do a couple more questions regarding isotopes, and then come back to this and teach you a bit more on that as needed. Okay, so the last thing about isotopes we need to know how to do is how to calculate that average atomic mass that we've been seeing this whole time on the periodic table. So you're going, how do they get hydrogen's 1.008? How do you get chlorine is 35.45? How do you get iron or copper's 63.55? How do you get those decimals, right? There's a way to get it. It's called the relative abundance or average atomic mass, okay? This is not your normal average. So if you want to do a normal average, force yourself not to, because you're going to get it wrong every single time. Okay, it's talking about relative abundance. So relatively in this room, we had, I can't remember the exact count, we had about 50% juniors, 50% sophomores, okay? But in my next class, I have about relatively 85% sophomores, and then 15% other, like seniors and juniors, okay? So the relative number is relative to your population, right? So relative abundance in chemistry is relative to all the elements of your cell, all the atoms of your self, your element. So what you have to do, what scientists have to guesstimate is, of all the atoms in the world that are oxygen, you have to count how many are 16 in terms of their mass, how many are 17, how many are 18. The trick is, I don't have to count them anymore. I know who's in most abundance. What's the atomic mass of oxygen? 16.00? Okay, I guarantee you 99% of all the oxygen atoms in the world weigh 16 grams. There might be 0.5% that weigh 17 grams and 0.5% that weigh 15 grams. So the majority rules, just like in here on the periodic table. So of all the fluorine atoms in the world, of all the fluorine in the world, what do you think is the majority player here? Ones that weigh 19. There's going to be a couple that weigh 20, a couple that weigh 18, but you're looking at the majority. So of all the zinc atoms in the world, what do you think are some of the masses? Look at zinc's atomic mass, it's what? 65.39, right? So you have a lot of them that weigh what? 65, but you got a couple more actually that weigh 64 and 66, because that's how you bring that decimal into play here. More that weigh 66 than 64 because it's pulling it up, it's pulling above 65 grams. So let's learn how to actually use those percentages and actually calculate our own and go with it here, okay? So I just have an example here. You can see I have water, looks like water, yeah, Mickey Mouse, but upside down. These hydrogen atoms here, and here, they're of the hydrogen isotope 1, because it's hydrogen with a 1 mass, right? But these here, these two oxygens, those are two different isotopes of oxygen. This isotope is number 16, and this is oxygen isotope 18. That's going to vary in their stability, therefore their percentages in the world, okay? You don't have to write this part down, but I am going to talk through relative abundance. So here's the facts here. You know, we can see the weights are different because of the mass of the neutrons, 18 and then 20. So what I'm telling you though is the 16, that one oxygen 16 is far more abundant than anything else, which is why the atomic mass on the periodic table is 16. 99.8% of water is going to have that oxygen 16 in it. Very, very, very little water is going to have the oxygen 18 in it. So you can see that kind of proves our point. Okay, so right here, that's the only part I want you to write down for this one. Whenever you are trying to calculate average atomic masses, then you're going to be using percent abundance. That's also termed relative abundance. So it's going to tell you in the problem, percent abundance or relative abundance. And then you have to utilize that to calculate your average atomic masses. I don't want you to be confused by the words percent abundance anymore. I want you to know what that means. Main goal of this slide here. So percent abundance is the same thing as saying relative abundance. All right, we'll do 2 or 3 problems on this, and then we're good. Okay, relative abundance, here we go. So let's calculate using chlorine's information as I have given it to you, and let's calculate the average atomic mass of chlorine, okay? So using this information, we're going to do that, and I'll kind of walk you through the first process. And I'm going to go full screen here. So the answer we can see is here, 35.453, which is what the periodic table says. But how do we do it? What you do is you take the exact weight of isotope number 1. So isotope number 1 is this 35 one. But that's the mass number. We want to use the exact weight. So we're going to say 34.968852. That's in AMUs, or atomic mass units. And we're going to multiply this by its percentage, its relative abundance percentage. This is already in percent right here, but we can't use the percents as is. We have to take them back to their decimal form. So we can't multiply by 77 or 75.77. We have to multiply by the decimal, I'm going to say the decimal version, which is 0.7577. So back it up the two spaces you did. Remember, percents are times 100. You're just backing it up without the times 100 part. So then this one's going to be 0.2423. Okay, so take your first isotope, multiply by its percent abundance in decimal form, 0.7577. Don't do anything with it yet, but you're gonna equal that out. I'll look at that number. I have it written down, not in front of me. I'll calculate it again if I need to. And then you're going to do the same thing for these second isotopes. So you're going to take isotope number 2, and its mass is 36.965903. Normally I won't give you this many decimals, okay, just because that's a lot to write. And you're going to multiply by its percentage in decimal form. So that's AMU. In decimal form, 0.2423. Darian, did you get the first one? 26, is what you said?
Yeah, 26.5108016.
Okay. All right, so that's the first one, and then the second one?
895688829.
Okay. So once you get both of those, all you do is add them together. Add them for me.
35.467639.
Okay. You see how this number, 35.467, is really close to this number here? They should be. Whatever you get in terms of your calculation of your first multiplication, your second multiplication, when you add them together, that is the average atomic mass of chlorine. It should be really close to whatever the periodic table says, or if I give you a given, it should be really close. And you can always verify you're right, because you should be really close. But if I said, okay, I have two unknown isotopes, isotope number 1, isotope number 2, and these are their masses and these are their relative abundances, and I said, okay, determine the identity of the element, and you get here, you could identify it as chlorine. What do you have to do? How do you identify this as chlorine if I didn't tell you it was? You just look on the periodic table for whichever one is closest to 35.4 something. So I could give you it two ways. I could give you the true identity, calculate atomic mass, or I could give you some information. You calculate the atomic mass and then find out the true identity, just basically by using your periodic table. So this is stuff that you just keep in your calculator. I like to see this work at least. Okay, so let's go ahead and do this one first, and I think I'll be done here. There are 3 common isotopes. You guys need to work through this problem with me, so you have an example for later. Thank you. There are 3 common isotopes of boron. Boron 11, which weighs 10.998 AMUs. Is that on the bottom of your paper?
Yeah.
Thank you. Good. So show your work down there, okay? Number 1. Boron 11, which is 10.998 AMUs. Boron 12, which is 12.011 AMUs. And boron 13, which is 12.99 AMUs. It tells you the relative abundance of each. What is the average atomic mass? Tell me how to start. Any takers? The more you guys participate, the faster we get done.
10.9.
Okay, so this is isotope number 1, right, which is the boron 11. So this is an AMU. Keep going. So why do you say times 0.92? Right, they gave you the percentage, and you have to back it up 2 decimals because you've already multiplied by 100, and I want you to get the decimal version of that. So times 0.92, okay, we're going to get that. Next isotope is what? 12.011 AMU times what? What's that in decimal form? Keep going. 0.01, good, because you need to back that decimal up. Boom, boom. So there's a 0 in front of that 1 whenever you back your decimal up. So 0.01. And then the next isotope, 12.99 AMU times what? Say again. 0.07, right? So 7%, back it up 2 decimals, 0.07. So 0.07, and we're going to get that. So in your calculator, you would calculate this one to be 10.118 AMU. This one would be 0.120 AMU. And this would be 0.909 AMU. And I went to, let's see here, I went to 3 decimals on these two, and then this one went to almost 3. I don't want to round too soon, because I do not want to have problems with my sig figs later. But anyway, once you get here, just add them up. That's it. A lot of people will add them up and then divide by 3. I'm like, no! You've already kind of, quote, divided by 3 when you do this whole percentage business going on here, okay? So do not do your normal average stuff. Do your percentages, get it, add it, that's it. So that's about 11.147 AMU. What is the average atomic mass of boron on your periodic table? 10.81. I probably made those numbers up. That's why that's not incredibly close. I should have probably been more accurate, but it's fairly close to what we got here. So I would say that's 11.15. Cool. Okay, so you guys are going to complete an activity lab. Basically, you have this awesome isotope called benium. Like all the other EMs, chromium and vanadium. We have benium. Benium comes in 4 isotopes. They're pinto beans, lima beans, black eyed peas, and kidney beans. So lovely 4 varieties. They all have slightly different masses because they're isotopes, right? So they have a different number of. They're isotopes, so they have a different number of neutrons, okay? You're going to determine the average atomic mass of benium. You're going to be utilizing this method to do so, but you have to get their average masses first, okay? This is teamwork, made the dream work. That's the situation. You have scales. You are going to have to count out and separate your beans into individual sections first, and then you guys are going to do the math. It's really simple, but it's a really easy lab grade, okay? After that, after some people are starting to get done, I'll warm up the 3D printing pens, and you guys can try some of that out. You can also start your homework, okay? So, you guys got to be active with me in the morning, because we should have been done with this like 15 minutes ago. So, the more you can reply to me, the better. I have your lab groups for you. They're on the board now. No goggles required, okay? So, you guys, you'll see your new lab stations. I changed every single unit, so. Cool? Go with it. It's called benium. It's probably like the 10th page, 11th page in your notebook. Is everybody up there?
There's 2 Madisons. I don't know.
Ooh, I did that the other day too. Let's see where the other ones are. You guys can decide. 3 or 7. Because it's Madison. Maddie Lewis is going there. That's what she is. Oh. You guys, here, Maddie Lewis go to 3, and then you go to 7. Okay?